Hi, welcome to the talk of our paper, Evaluating Logical Generalization in Graph Neural Networks. This is a joint work with Shagun Sudhani, Joel Pinu, and William L. Hamilton. Now, we are interested in the task of relation prediction. So in relation prediction, we look into the task of inferring relations between object and entities in a knowledge graph setting, where relations can be composed of multiple relations. Now, before we go into the task, let me talk about some key requirements that we look for when we talk about generalization. So in generalization, we are mostly interested in compositionality, which is the task of inductively reasoning to unseen compositions, in our case, unseen relations. And we are interested in the task of meta-learning or transfer learning, where the task is to learn to adapt to new data, and also lifelong learning, where the task is to remember the prior data. So these are the three key desideratas for generalization. And in our task, we look into the task of logical reasoning. So when I talk about logical reasoning, I mentioned the fact that relations can be defined using first order logic. So for example, son of a son is a grandson, and this is a first order logic rule. And what if we generated graphs using a bunch of these rules? So then we will get a nice data set for relation prediction. This data set will be diagnostic, and this data set will help us to evaluate precisely on how our models are generalizing. That is exactly our proposal. Our proposal is GraphLog, which is a world consisting of multiple knowledge graphs, where each knowledge graph is its own world, which is built using a set of first-order logical rules, such that each knowledge graph is grounded in propositional logic. Now the setup is quite simple. We built a set of rules, which are a set of first-order rules, and then we divide the rules into a set of worlds, and then we generate graphs based on each world rules. Now the features, there are multiple features of GraphLog which we are interested in. Most prominently, GraphLog is the only data set where you can perform supervised meta-learning, multitask learning, as well as continual learning on graph domain data. So in order to build this data set, we use a simple procedure of rule generation, where we randomly sample rules of the form of Ri, Rj, and then we make sure that the rules are consistent. Then we sample the rules in an overlapping fashion, such that each world has a set of common rules from the previous world. And then we generate the graphs. The graph generation process is a bit more involved, and I ask you to read our paper to learn more about it. Now we end up with 57 logical worlds, and each world contains 5,000 training graph, 1,000 validation, and 1,000 testing graphs. Now we also built a few baselines to work on this set of rules. Our hypothesis is that a model should learn representations that are useful for solving the task in the current world, while being general enough to be effectively adapted to the new worlds. So essentially, we propose a representation and composition function, which is a two-way network, where the first network essentially looks into the graph and gives out the relation embeddings, whereas the second network takes those relation embeddings and then predicts the type of the relation between two source and async nodes. So we look at few state-of-the-art models for representation and composition functions, which include GCN, GAT, RGCN, and HGAT. Now we present few results. So in case of single task learning, we find that our set of worlds can be easily segregated into worlds based on difficulty, and that is based on the accuracy of each test task. Whereas in case of multitask learning, we find that if we increase the number of worlds, the accuracy decreases because of model capacity saturation. Now we also did multitask learning and adaptation based on difficulty, where we find that training on diverse and difficult set of worlds gives you better scores in terms of adaptation. Now we also test for continual learning on graphs, and the way we set up GraphLog, testing on continual learning is very precise because you can evaluate the similarity between the worlds. And we find that in overlap scenario as well as in a curriculum learning scenario, the performance of all the models decrease, and the performance of the past accuracy is also pretty bad. But we haven't tried any curriculum learning specific algorithms, so this is an open problem for you to try on in graphs. So the key takeaways are training on diverse dataset improves generalization performance, pre-training on diverse and difficult dataset enhances the model's ability to adapt, and lots of work are needed in lifelong learning for graphs. So we release our code in Facebook Research/GraphLog. We also release our code in a pip installable file, pip install GraphLog, which gives you all the data loaders that you would need to work on multiple different graphs. So thank you for listening to our talk. If you have any question, feel free to ask us during the QA session or feel free to read our paper.